right, so we are going to continue our exploration of rates of change, in particular looking at tangent lines. So a tangent line is a line that is representative of the slope of a line to a curve. So what we're going to do is use limits to go back to what we started talking about in chapter 1, which is instantaneous rates of change, and now we're going to apply it. So at the beginning of chapter 1, we talked about rates of change. We talked about the average rate of change, and we talked about the instantaneous rate of change. And we looked at getting closer and closer and closer to finding it. And that's when we used our tables, and we looked at the numbers to the left, the numbers to the right. What we're actually going to learn now is how to not use a table and how to algebraically find the limit to the left, to the right, or actually at that point. So that involves something called the difference quotient. The average rate of change, as we previously discussed in 1.1, represents the amount of change of a quantity over a period of time. So an average speed for a vehicle is the change in miles over the change in time. So average speed is always the easiest one to talk about because you see it in your everyday life. Your driving speed comes from the miles you've driven over the time it takes you to drive them. Another one to talk about is average temperature. You can look at the temperature at 8 a.m. and 8 p.m. and talk about the average temperature of the day. Average rates of change are the change in an interval over the change of the length in the interval. In mathematics, the triangular symbol delta represents the word change. So in math, the triangle symbol delta represents the word change. So we have delta y over delta x, which is change in y over change in x. We have most predominantly seen that using slope. So if I gave you a function and I gave you an interval and I said, find the average rate of change of that function over the interval 1, 3. So that would be like me telling you to find the slope at the point 1 and 3. So that's just a different way of asking you to find the slope of the curve at 1 and 3. Mainly because it's not really slope, so to speak, because it's cubic. So what you would do, to find that average rate of change is take f of 3 minus f of 1 all over 3 minus 1. Change in the quantity or change in the function over the length of the interval of the function. So f of 3 minus f of 1 over 3 minus 1. So I need to know, okay, what is f of 3? So f of 3 is 3 cubed minus 3 minus f of 1, which is 1 cubed minus 1, all over 3 minus 1. So 3 cubed is 27. 27 minus 3 is 24. Minus, well, 1 cubed is 1. 1 minus 1 is 0. So 24 minus 0, all over 3 minus 1, which is 2. 24 over 2 is 12. So the average rate of change of f of x of x cubed minus x from 1 to 3 is 12. Not that that means a whole lot, but that's what it represents. Sometimes we cannot find particular points. So what we do is describe the rates of change by looking at slopes of secant lines. So secant line slopes represent the average. Secant line slopes represent the average. The slope of the secant represents the average. One more time. The slope of the secant represents the average rate of change. A secant line to a curve is a line that passes through 2 points on the curve. We find the secant line using f of x minus f of x1 over x2 minus x1. We call that the slope of the secant. The slope of the secant represents the average rate of change. That will not leave your head today. A tangent line is the instantaneous rate of change. A tangent line is the instantaneous rate of change. It is the limit as the difference from x2 to x1 gets to 0. So it is the limit as the difference from x2 to x1 goes to 0. A tangent line to a curve is a line that touches the curve at one point. So we find the tangent line slope by looking at the limit of the secant line slope. Find the tangent line slope by looking at the limit of the secant line slope. That's what we did in the warm-up exploration in part 8. So in the warm-up exploration, when we found those points, 3, 4, and 5 all represented secant line slopes. 8 represented the tangent line slope. So in that exploration, when we found the slope between points, we found secant line slopes. When we found the actual limit as it approached 1, we found the tangent line slope. So graphically, and I know yours is a little harder to see because it's not in color. Graphically, what we have is a secant line and a tangent line. So in this diagram, this line right here which I'm off a little bit, represents the equation of the secant line. That line is the slope of the secant line. It is the change from point A to A plus H and up H. So the green is the secant. The purple is the tangent. Can you see how the green touches twice, the purple touches once? The green touches twice, the purple touches once. So if the green touches twice and it represents the difference from point A to A plus H, what does the purple represent? Well, it represents the difference from A to A plus H, where H is 0. Because the distance is infinitesimally small. So take a minute, read that paragraph, and try to make the connection without me kind of shouting it at you. So what those directions are saying is what we did in the exploration. We wanted to find the slope at 1, 1. So then we looked at 2, 4, and then we got closer and we looked at 1.25 and whatever that number was. We got closer and closer and closer. So in here, we will always calculate our secant lines, no longer using the slope as we knew it in the past, but the slope formula we know today, which is going to be f of a plus h minus f of a all over h. So that creates the slope of a secant line. The tangent line wants the h to be infinitesimally small, so we're going to make our h approach 0 and put 0 in our denominator. So this is when we end up with 0 over 0. We know we have to do some algebra, and we get it down to a number. F of a plus h minus f of a all over h is commonly known in mathematics as the difference quotient. So if you hear your textbook or myself refer to the difference quotient, that is f of a plus h minus f of a all over h. So there's biologists who like to study the growth of populations. An easy population growth is fruit flies. Fruit flies grow exponentially fast and then are horrendous to get rid of. So the following represents the number of fruit flies that grew in a controlled 50-day experiment. We're given the points 23, 150 and 45, 340 from the graph to the right. Compute the average rate of change, or AKA the slope of the secant line, created by these 2 points. So again, the idea in this case is that f of a would be represented by f of 23, and we know that that's equal to 150. The f of a plus h would be represented by f of 45, and we know that that is equal to 340. So the h value is the difference from 45 to 23. So if it asked you to find the change, that would be f of 45 minus f of 23 over 45 minus 23, or 340 minus 150 over 45 minus 23, which is 190 over 22. Which is approximately 8.6 flies. So it says, compute the average rate of change. So what that means is that there are 8 flies essentially growing per day. So what that means is on average, the rate of change is changing by 8 flies per day. You could also have said 9 flies because you got 8.6. So they would have accepted. You could also have said 8 to 9 flies per day, allotting for the fact that it's 8.6. Because again, we don't talk about flies in 0.6 percentages. So you could say 8 to 9, 8 or 9. Now, if the question changed and said, how fast is the population growing on day 23? Well, if you look at that original set of points, does this slope of this line look like it actually represents the slope of the line at this point here? No. So like think about if I asked you to just draw in slope at a point here, you would try to draw it in as close to the graph as humanly possible, right? At this point here, the slope looked like it almost tears off. It's kind of like, oh, the population reached its max capacity, so it stops growing. So what happens is that at all points on the graph, the slope is ever changing. So if I looked at these 2 points, oh, that does not accurately represent the slope here. The slope here is much steeper. So how do we get a better or more accurate prediction of that steeper slope? Well, we do what we did in the exploration. We pick points closer and closer and closer to that point. We don't have an equation for this graph. So what we have to do is try to pick points near it. So what I would do is look to the left of it and look to the right of it. So I would, in particular, select maybe 25, because that's 2 to the right. So I'm going to find f of 25 minus f of 23 over 25 minus 23. And at f of 25, it looks to be at about 175. And again, you're predicting. There's no particular points on there. So 175 minus 150 over 25 minus 23. So you get 25 over 2, or 12.5. Should it not make sense to me that there are more flies growing as my slope is closer? Yes, because we said the slope was steeper. So it went from 8 to 9 flies a day to 12 to 13 flies a day, much higher. So how do I look even, maybe closer? So maybe we pick a point, what? Closer. Yeah. So you could pick closer, which is 24. You could also go below it and look at that point. Because remember, we like to look at the limit from the left and the limit from the right. So let's look at 24, and then we're going to look at 22. Go away, lines. So maybe at 24, it's hard to say, but I'd say 160. Which maybe that's a little low. I'll go 165. So 15 over 1. And then maybe look now. So we do 25, 24. We're not going to look at 23. So maybe we look at f of 23 minus f of 22. So 23 is 150. 22 maybe 140. And we get 10. So again, you're predicting. It's hard to get precise, but we could say on average, there's probably 13-ish flies growing per day at 23, because we had 12, we had 15, and we had 10. So you get like the average of all three. Typically, they would give you numbers so that you are getting more precise values. Like in the textbook problem, they'll give you some numbers. Okay. So I'm going back to the exploration now. But now we're going to do it with the limit and the difference quotient. So we did it previously with the function at the point. So there's two difference quotients in calc. There's the f of a plus h minus f of a all over h. And then we have the other one, which is f of x minus f of a all over x minus a. So that's what we did in the warm-up. So we did the limit as, that's hard to see, x approaches a of f of x minus f of a all over x minus a. So where f of x is your function, a is the value at the point, so we did f of 1, and then we did x minus 1. So this is what we did in the warm-up, where a was 1, f of x and x are the function in x, and then we got that. And do we remember what we got for our answer? 2. So now we're going to do it with the difference quotient using a and h. So we can also look at it using the limit as x as h approaches 0 of f of a plus h minus f of a all over h. So again, both of these represent the same thing. So now let's look at it. So a plus h is going to look like a plus h squared minus f of a, which is a squared, because you're plugging a plus h and a into f of x, all over h. So algebraically, if we have a value, in this case, my a is 1, right? So now we could look at this and say the limit as h approaches 0 of 1 plus h squared minus 1 squared all over h. In order to simplify, I have to take 1 plus h squared, and I need to FOIL. I have 1 minus 1. So 1 minus 1 is 0. Now we're left with the limit as h approaches 0 of 2h plus h squared all over h. So what do I notice about both terms in the numerator? They both have an, so I can take out a. Leaving me with the limit as h approaches 0 of 2 plus h. Finally plugging in 0 for h, I get 2. And I kind of dragged that out. You don't have to show every one of those lines every time. It says to find the equation of the tangent line to the parabola at the point. So that was that last part of the exploration we did. The equation of the tangent line is y minus y1, slope x minus x1. So the equation of the tangent line is y minus 1 equals 2x minus 1. Again, you can leave it in point slope form, or you can simplify and get it into slope intercept form. Both are correct. That green equation represents the equation that goes through the point on the graph. So again, if here's my curve, y equals x squared, here is the point 1, 1. That green line represents, didn't touch, the slope of the tangent line to that curve. So it represents the line that hits the curve once at that point. What if I didn't want to know the slope at 1, 1? What if I want to know the slope at every point? So now I want to know the general slope. I want to know at 2, 4. And then I want to be able to calculate it at -3, 9. Like, I want to be able to calculate the slope of the line at any point. So what we do to find it at any point is not plug in a value for a. So what we do is we find the limit as h approaches 0 of a plus h minus, a squared all over h. So in this case, you find f of a plus h minus f of a all over h in general. So the a value being left in is finding it in general. So remember that this represents the slope of the tangent of x squared at any point a. That's what we're finding, the slope of the tangent of x squared at any point a. Okay, so let's calculate it out. So in math, we have something called Pascal's triangle. Pascal's triangle is a simplified way of calculating our terms. In particular, Pascal's triangle works most for x squareds and x cubed. So this represents x plus h squared. This would be x plus h cubed. And the values of the numbers in Pascal's triangle represent the coefficients that go along with it. So essentially what happens is whatever the first variable in your term is, its power matches this power here. So it's x squared, then it decreases by 1, so it's x to the 1, decreases again to become x to the 0. Here, if we're looking at something cubed, then this is x cubed, then x squared, then x to the 1, and again, x to the 0. We know anything to the 0 power is simply just, so you don't even have to really worry about writing in the x to the zeros. So I'm going to change these to y's just because I hate h's. It doesn't change anything though. How do the h's come into play? Well, the h values go up or down in the opposite direction. So if the x squared starts on the left, then on the right, we start with y squared. Then it meets in the middle as y, and then y to the 0, which again we know to be 1. Similarly, y cubed, y squared, y, no y. So that works for all functions. The coefficients always go 1, 3, 3, 1. An example with a cubic and numbers would look like this. So if I gave you 2x plus 3y cubed, instead of having to FOIL that twice, we now would know that it goes 1 times 3 times 3 times 1. You start with this term and you'd cube it, so it would be 2x cubed times 2x squared times 2x times 2x to 0, aka gone. Starting over here, it would be 3y cubed, 3y squared, 3y, all to the 0. So this, all cubed, becomes 2x cubed plus 3 times 3 is 9, 2 squared is 4, 36, x squared y plus 9 times 6, xy squared plus 27 y cubed. And now you don't have to FOIL it 3 times. That's how when I do these right here and I like write my a squared plus 2ah plus h squared so quickly, it's because I know it's the 1, 2, 1 from Pascal's triangle. Okay. So then going back to this, we have the limit as h approaches 0 of a squared plus 2ah plus h squared minus a squared all over h. Cancel out the a squared and the a squared. That leaves an h in both terms remaining, so take out an h. Plug in your limit value of h and you get 2a. So what that means is that at any particular point on the curve x squared, the slope will always be 2a, where a is any point on the curve. The slope will always be 2a, where a is any point on the curve. So I think that's the end of day 1. Tomorrow we come back and reiterate it, and then we also talk about something called the normal line. So we're going to go to our textbook for the homework. And then again, you can see like for 9 to 12, you're going to leave space because we're going to do parts B through D tomorrow.